In this video, I'm going to go over activation functions and loss functions. So we've been through neural networks and we've been through convolutional neural networks already, and we've also seen how they update weights due to backpropagation. But there's still this little missing piece of the puzzle that we need to discuss, and then we have a full understanding of everything we need to devise our neural networks. So I'm going to take you through an example now that explains why activation functions are going to be necessary. And this is called the XOR example. And this is just for a very, very simple neural network. For XOR, we will have just a data set of just 4 points. And the idea is this is meant to be an explicit OR. So you can have either one or the other, but not both. Which means that 0, 1 and 1, 0 should both go to 1. And when these two numbers are the same, they should go to 0. And there is a solution for this when we have a nonlinear activation function, but very, very interestingly, there is no solution unless we include these activation functions. So this is going to be an example why we need a nonlinearity at every single layer to increase the amount of generalizability that this neural network is going to have. So remember, for a neural network, we are going to have this for each layer. It's going to be W transposed X plus B, and this is going to be for the hidden layer. So these are going to be the hidden weights, which in this case are just going to be 1, 1, 1, 1, and the bias is going to be in blue here, so that's going to be 0, 1, again for the hidden layer. And then to get your output, you're going to take what you get from your hidden layer, and you're going to, so if we've got H here, you're then going to do the exact same thing with H, so you get W for the output times H, so this is all H, plus the bias for the output. Okay, so let's go through what happens in this case, and I'm going to take this opportunity to show you how we can process the entire data set in one equation rather than doing each one individually. So what will happen is we'll take our weights, which are going to be W11, W12, etc. So in this case, it's just going to be 1, 1, 1, 1. So this is WH, and then instead of, maybe I can draw it here, it's WH. Instead of just a little x, we're going to do the entire data set at the same time. So this is going to be 0, 0, that's this one, and then 0, 1, 1, 0, and 1, 1. And then we do a matrix multiplication of these. So remember, with matrix multiplication, we're going to go across in the first matrix and then down in the second one. So you can see here, maybe I'll do it in red. Oops. We will have 1 times 0 plus 1 times 0. So this top one is going to be 0. then we're going to have 1 times 0 plus 1 times 1. And it's going to be where the row crosses the column. So in this case, it's going to be 1. And then you can see it's going to be the same here. And then 2. And we do the exact same thing with the next one. And because it's 1, 1 again, we can see that we're going to get the same outcome. So that's this bit done. We now need to add the biases, which is going to be, I'm going to do in blue. So that's going to be plus this 0 minus 1. So it's going to look like this. So we end up with just 0, 1, 1, 1, 2 as before, but minus 1, 0, 0, 1 here. And then when you put that, so this is what goes into the next layer. So this is going to be multiplied by W0 and then added to B0. B0 is 0, so we don't need to add anything. But this is now going to be multiplied by, I'm going to do it here. So it's going to be 1 minus 2. And that is going to equal, so now we're just going to get a 4 by 1. So it's just 1, change color again. It's just going to be 1 times 0 plus minus 2 times minus 2 times minus 1. So it's going to be 2. And then 1, 1, and then 0. And these are going to be our outputs. So you can see from our labels we should have 0, 1, 1, 0, but we've actually got, maybe red was good. We've actually got 2, 1, 1, 0. So it's going to be, it's very, very close, but there's no way for us to actually change this 2 to a 0 without also changing these ones or this 0. And that's a very, very big problem because we're limited by the actual capability of the network, not by our ability to train it. So this is why we need to have some sort of non-linearity to go from a linear set of functions to a non-linear one. And it is actually a very, very simple one that can actually solve this problem for us. So if we have any number z, it's going to be at this stage. So anytime we come out of a layer, we can call that z, or we can call it h. Maybe I should call it h for this. We are going to take the Relu. So this is the rectified linear unit, and that is equal to the maximum of h or 0. So if it's negative, it just goes to 0. If it's positive, it stays the same. And if it's 0, it stays the same as well. So what's happening in this case is this is our h. So you can see from all of these that we have only one negative thing. So that's the only thing we need to change here. So we just do the very, very simple, pass it through this function, and this is going to give us a 0. And now when we multiply by the same weights, which I shouldn't have got rid of, this is 1 minus 2. So now we're going to have a 0 here. If I just go in purple this time, we're going to have 0 times 1 plus minus 2 times 0, which is 0. Then everything else is going to be the same because it's the same calculations we did before. So this is 1, and this is 0. So now when we have Relu, we get 0, 1, 1, 0. So this XOR problem is only solvable when we include these nonlinearities. So that's the reason that we have them. And in neural networks and machine learning, we usually are going to be using this Relu or something very, very close to this Relu. So more recently, the idea of Leaky Relu has come out, and so this is the regular Relu function. Instead of that, they just do a very small decline in the negative, just so you still get some of the information from negative samples. It doesn't matter that much. The only thing that's important is that there's some sort of nonlinearity involved. So that's what Relu is giving us. There's some other functions that you can consider, like the Tang functions. I'm not going to go into them except for the functions that we might need in the final layer, because you use a slightly different activation function in the final layer, because there's some nice properties that they have. So let's have a look at them. So in the first case, when you have two classes, so similar to what we had before, we have two classes, so we only need one output node, and this is either a 0 or a 1. So this is the output. When we only have two classes, we use this term called binary cross entropy. And in that case, the activation function of the final layer is going to be called the sigmoid function. So that is this function. And same as a lot of stuff that we've talked about before, you simply do one line of code in Keras and it sorts this out for you. So you don't need to memorize this function or anything. I do want to now also talk about how this relates to the loss function though. So that's what I'm going to go into now. So the important thing is this function right here. And this is called the loss function with this squiggly L. Remember when we were talking about backpropagation? If you have in your final layer a label and it should be 0, and so this is your last layer of the neural network. When you go backwards through the network, we do this. We're interested in the error, which is the difference between what you should have got. So sometimes it's called a cost function or an error function. This is exactly what we are talking about. So you'll pass back in the loss of your actual outcome. So if your probability was 0.7 here, you would just pass in the loss of 0.7. And then that defines how you learn your weights. So this is really, really crucial part of the network to design. So I'm going to talk about how this works when we have two classes. So firstly, if you haven't seen the logarithm before, it looks something like this. So notice that because we're dealing with a probability, and this is going to send, the sigmoid is going to send everything to somewhere between 0 and 1. You are always going to have a negative here. So this is why we have this negative function at the start here. That's just the reason for that. It can be a little bit confusing when you first see it. So this log function is going to map everything to a negative value between 0 and 1. and we'll see why that is useful. So yeah, let's again say that you have this final output layer in your neural network, and let's say that the label y is equal to 1. And you've got 0.7. So you found that the probability, if this is the likelihood of someone having a disease, you found that the probability of them having it is p equals 0.7. So you would usually round that up to 1 and say that it's true. But the probability that the network sees is going to be this 0.7. So in this case, because y is equal to 1, 1 minus y is going to be 0. So this whole part of the equation gets cancelled out. And we just have 1 times log of 0.7. So that's going to be here. And remember, we have this minus sign, so it's actually going to be here. Okay? But if we are wrong, and this y is equal to 0, so the true label is 0, then we look at the other half of the equation. So now this y is 0, so it's going to get cancelled out. This is going to be 1 minus 0 is 1, and this is going to be log of 0.3. So now you can see that this is much bigger. So this, once we do the negative sign, it's going to be up here. So this L is going to be much bigger. So when we send this back into the from the loss function into the backward pass of the network, the loss is going to be much larger, which means that you're going to end up with larger gradients, and you're going to be looking for a bigger shift essentially for all of your current weights, because you're not doing as good a job. And we do this for every single data point in the entire database, and add all of these up. So this will be the sum of all of these points. When we have more than one class, so for example, when we were dealing with the MNIST dataset, and you've got the number 7, and it's going to go through a neural network, and you end up with 10 points. So there's 10 of these. Then you're going to have to use categorical cross entropy. Categorical cross entropy as a loss function is very, very similar to binary cross entropy, but it's just an extension of it for multiple classes. So I am not going to go into too much detail there because it's going to be very similar to what we've already seen. But I'm going to spend a little bit more time talking about the softmax function, which is an extension of the sigmoid. So the sigmoid is the same sort of ideas as we're going to see now. So again, exactly the same thing. In your final layer, you'll just use this softmax function, which is one line of code in Keras, instead of a Relu or a sigmoid when you have multiple classes. And what this function is going to do, we've all heard a lot about these exponential functions with coronavirus. So again, I don't want to talk too much about them, but they're going to look something like this. And you can see that the bigger you get, the more it's going to scale this up. So doing kind of the opposite of what the log was doing. But let's say in our example, we have 6 data points, and we've just got, let's say at the end, we've got 1, 1, 1, 5, 1, 1. So first let's look at what would happen if instead of this we just try to do a regular normalization to get this down so that everything adds up to 1. So we need this all to add up to 1, and we just do a regular normalization, which is going to be this number divided by the sum of this number. So instead of any exponentials here, we are just going to have, these are all going to be some sort of z, and it's just going to be zj over the sum of zk. So what's going to happen here is we sum all of these up. So that's 1, 2, 3, 4, 5, plus this 5. So this is going to be 1 over the sum, which is 10, and then the next one's going to be the same, etc. And then we get a 5 over 10, 1 over 10, 1 over 10. So that would be our probability distribution for this example. But now if we use the softmax function in the top left corner, then we get a much more polarized outcome. So I think some of you won't have seen this E before. So we have E equals 2.71 or something like that. I'm just going to show you what happens for the example if we, instead of an E here, we just have a 2. So we are going to do 2 to the power of zj, which in this case, this is zj. So that's going to be 2 to the power of 1, which is 2. And then we have exactly the same, exactly the same. Now we have 2 to the power of 5, which is 32. And then 2 to the power of 1 again, and 2 to the power of 1. And then this denominator is going to be the sum of all of these. So we're going to have 32 plus 5 lots of 2, so it's going to be 42. And that's going to be the case for all of these points. So now you can see the difference that in this case, the ones that we're less sure about have gone from being 1/10 likelihood to somewhere around 1/20th likelihood. But this 5 has gone from being 50% chance to being something like 75% chance over here. So, and this is exactly what we want from the softmax function. It's there to make us more confident of our score and more effectively. This means that we're going to get much more polarized yes or no for each of these classes, and that's going to allow us to train a lot quicker and a lot more effectively, because these are then going to go into the loss function, which means that the gradients are going to have the gradients that we compute are going to be a lot less fuzzy because we're more resolute in our prediction rather than sort of sitting on the fence a lot. So yeah, we're trying something wholeheartedly rather than being a bit more half-hearted. So that's everything for this video. There are some additional loss functions which I'm not going to go into too much detail, but if you want to explore, then please do.